Oh, thank you, Bushan, and I've enjoyed working with you over the years too. So, so we're here after lunch. I hope this isn't going to be too sleepy a session. The title of the talk is Building in Quality 10 Years Later. And I was a little surprised. I made a couple submissions to the conference, and I was a little surprised that this one was chosen to compare practices for building in quality rather than testing in quality. So you've probably all heard the saying, it's better to build in quality than test in quality. But what does that mean to you? Do you have any people who've thought about that?
Do it from the beginning rather than
Yeah, do it from the beginning.
Design matters.
Design matters. Other thoughts?
It kind of goes with the saying, you can't test the wings back onto an airplane.
You can't test the wings back onto an airplane. Ooh, good image there. So I've been coming to this conference for many years, and I worked at Hewlett Packard for a long time as a developer, as a quality engineer, as a process expert, and some various other jobs. And over the time, I did a lot of testing, and we find that there's a lot written about testing. When you say quality, the first thing many people think of is testing, and so you have this big pile of testing books. There's a lot fewer books about how to get quality into a product from the beginning, and especially ones that take a holistic view across the entire life cycle, which is what I want to talk about today. I gave a paper on this topic 10 years ago at PNSQC. At that time, I was talking primarily about defect cause analysis and how you use that to select processes or practices that will work at different points in your life cycle. That paper is still out on my website, and I didn't want to go back over the same territory. Wanted to take instead a deeper look at how quality is built in, and to talk about differences that have come up because of the Agile development methods that have come into play. Does anyone know if that camera is live? Because there's no human being there, is it still recording?
Yes.
It is. Okay.
Can you take the tag off because place some time?
Yeah, you think that's some cause issues? Okay. Yeah, okay, hopefully we're good enough. So, how many people here are mainly testers? There's some of you. And how many people here are mainly developers or scrum masters or project managers, that kind of job? And I've apparently missed some because there's some people who didn't raise their hands. Maybe you came because the lunch is good. Yeah, James Block's talk is I'm sure, a very awesome talk. So this talk's going to be more aimed at people who are starting from the development side. So we're starting from thinking about how do you get quality built in in the first place. And I've seen a fairly significant difference in practices in different fields. I've had the opportunity to work in high reliability as well as consumer field and web apps, and you see different things in use. So there's software that just has to work. You can't afford to ship it and have it fail and then fix it. So nuclear plant control, that'll work the first time. Don't need another 3 Mile Island. Aerospace, as he said, you can't have the wings fall off. Harder on the people who are in the airplane, also harder on the people below the airplane when it falls. And medical products, obviously, and cars. Cars and automotive in general has an enormous amount of software in it today, and we have high expectations for these things. You think about it. Have you ever had your car hang or freeze and you needed to reboot it? Anybody had that happen?
That's happened.
Yeah. I had that happen once in about 1996 on a Ford Aerostar minivan. The whole control panel froze and we had to turn the ignition key off and back on. Your experience?
It was actually one of the controls for the engine in a Toyota. And the car died.
While you were driving?
Yes.
Ooh. Mine at least was parked. But this is a sample of how often this happens. It's happened to me once, happened to you once,
Twice too many.
twice, over a period of years. So how many people had to reboot something on their laptop in the last week? Because it becomes yeah. So we have different expectations.
Sorry to interrupt.
Okay.
Can you turn your lapel mic on?
Oh, sorry.
There we go. Thank you.
Yeah, so we have different expectations for the high reliability software, and then we wonder, well, how are people who are making this, how are they getting this to happen? And so I started out working in a high reliability field and learned what we were doing, and that all seemed perfectly normal. And then I moved into a consumer product, and I found the practices were quite different. And the interesting thing was I found that an awful lot of the people in the consumer fields thought people in high reliability fields were spending an immense amount of money and time to get the results that they were getting. And that was not actually true. They were using different methods, and they were using some very different assumptions. So I'm going to talk about those because from what I've seen, if those assumptions were more commonly used in all fields, we would all have less work to do and better software. So the first one was just the fundamental belief about who owns quality, and we've had at least 2 speakers about that already at this conference. Where the places I worked, it was made very, very clear to us that the development team fundamentally owned the quality. The test team did not. In fact, the medical products organization I worked in did not have a separate test team. I did not see work in a place that had a separate test organization for the first 12 years of my career. They were all cross-functional teams, and this was well before there were Agile. This was in Waterfall, but we had cross-functional teams anyways. So you made it, you were responsible for it. It broke, the calls are coming in from the field, you will be taken off your current project and made to work on this until it's fixed. There's nothing like that for making you really enthusiastic about having high quality so that you don't have to have your weekends wrecked because something failed in the field, plus your current project is now way behind schedule. No fun. If there was a test group, it was clear. There were clear responsibility was assessment and good, solid, thorough assessment. Good information coming back from that test group, and information you could rely upon. So figuring out how to estimate how many more unfound defects there were, and that was commonly done. That was an expected competence in a test group, was to be able to estimate unfound defects. And typically you do find in a regulated, especially in any regulated environment or one that has like ISO 9000, it will have a quality policy in which the top management is responsible. That means if there's something really, really dire, the top management can be sued. And then there's this hierarchy where everyone has some responsibility, but I've never been fond of the we're all responsible for quality thing, because all too often that turns into nobody's really responsible. So the center's on the development team, and then the development team, being duly chastened by this and maybe a little scared, has strategies for how are you going to achieve this very high level of quality so that you don't kill people by mistake. So you start out with the idea, as someone else mentioned here, high quality from start to finish. So you're going to start out your project, every single step you take, every single artifact you make, you're going to ensure that it has high quality. You don't let the quality level drop. So you focus on finding problems as soon as you've created them. You fix the problems right away. And you'd think this is a no-brainer, but I have seen far too many teams that write software and then they've got someone else testing it and defects are flowing back to them, but they're cheerfully continuing to code on something new. That's not a practice you do in high reliability software. It's inefficient. And that's why we didn't do it, is that if there's a gap between the time you make it and the time you find out about the problem, you've got to go back and put your head back into where you were. And if it's weeks ago or months ago, it's going to be really hard to do that and time consuming. So you fix them right away. And then the most sophisticated one is you start thinking about how to prevent problems, how you could not make those mistakes in the first place. And this leads to really doing a lot of thinking about how defects are created. And this, again, was expected of people working in high reliability fields, that they don't think their whole job is about coding. So you're starting out with requirements, and what are some of the mistakes that you can make while you're gathering what the user wants? What kind of mistakes could you make?
Assumptions,
Make assumptions. They're possibly incorrect.
Small sample size for your customer.
Yeah, small sample size.
misunderstanding the request.
Yeah, you misunderstand the request.
Lack of test cases.
Well, you don't have test cases yet. At this point, you're simply going out and asking the customer what they want. What would you like to have? So yeah, you skip things that the customer wants. You didn't think to ask. You miss them. And you assume that they can actually tell you, which in a lot of cases they can't.
Yeah, one of my theories is the customer doesn't always know what they want. They always know what they want, they don't always know what they need.
So Brian's saying the customer may know what they want, but they may not know what they need. Very true. So you have a lot of assumptions at this stage. And then you take the things the customer said they want, you decide what you're going to build. Customer says they want a reasonable temperature in the room. You decide, am I going to build an air conditioning system or a heating system? Or maybe both. So it's like basic features. And you can make mistakes there by just losing requirements, basically. Or perhaps you're cheerfully building a heating system and the customer's actually in Puerto Rico. They probably don't want a heating system. They want an air conditioning system. And we move on to design. You know what you want, you're going to build. Now you have to think about what libraries are we going to need. Do we need an architecture? Do we need database tables? Do we need servers? La-di-da. This is one of the largest areas of errors and some of the more difficult ones to find. So these were ones we concentrated on a lot. Well, how do you prevent making design errors? You can both make logical design errors, you can have interfaces that don't talk to each other, you can have state machines that don't have all of the cases, and race conditions and all that kind of thing. But some of the nasty ones is those implied requirements. Oh yeah, it should work on every browser there is, including ones that haven't been written yet. Oh yeah, it should cooperate with Microsoft's various networks. Oh, including changes that haven't actually been created yet. So ignoring environment behavior is a huge cause of errors. And then coding. And I think we're probably all familiar with the kinds of mistakes you can make during coding. You're running off the ends of arrays and you're mixing up variables and all that routine stuff. Also maybe forgetting to do part of the design. I once tested a system that had it was a web system and it had things you had to set up as an administrator, but it didn't have any administrator screen. so yeah, that was one big fat defect report. Administrator can't do anything at all. I can go into the database and set that stuff up, but somebody's got to write that. And then today's programs, a great many of them need to be either installed or deployed, so that there's a whole set of files that need to be written to make that happen. Install files, make files, configuration files. Those are, well, they're not literally executable code like C or C++ or Java. They are code, and you can make mistakes there. So, I've seen people taking notes. There is a substantial paper in the proceedings for this, and there's about twice as much in the paper as I'll be able to talk about in 45 minutes. So just about everything I'm going to talk about is in the paper. So if you miss something. So what we would do in the waterfall days is to start out the theory early as possible. You do requirements, you're going to make mistakes, so you do reviews. Where you write down your requirements and you show the user, you see what they think. And so that's called a quality gate. And there's our little gate. So you started by setting up a quality gate there. And then we were so painfully aware that this doesn't work very well because there are so many ways you can miss an assumption, or the customer really wants something else and you don't have a way to know. So you write tests. And back in the old days, they were called acceptance tests or beta tests.
Today, the word acceptance criteria actually means something different, so it can be confusing. But the acceptance test was a test written, or a test to run by the user. You take it, you give it to the user, they run it, and they go, oh yeah, most of this is okay, but I hate this part. And so both of those were part of the quality strategy. And at this point, you usually started writing a quality plan, unless you started earlier, and say, yay, verily, we are going to have reviews, and we are going to have acceptance testing, and here's our rough plans for acceptance testing. How do we think we're going to get some customers who will use this without destroying whatever it is they're doing? And when I was working on cardiac care products, you can't have people just plain use the system unless you're sure that it's working. So there were various ways to basically Y-cable signals so that you had your new product and the old product, the old reliable product, both running side by side. So you have to think about that. How are you going, where are you going to get sample users and how many do you need? And lead to release. So, and then specifications, same thing. You have reviews, you have testing. At the specification stage is where you're writing non-functional requirements in the old days. And I mention this specifically because it's something that in a lot of people's transition to Agile, they've kind of lost those and not been sure where to put them. And so the non-functional requirements, what does the performance need to be? What does the reliability need to be? Things the customers usually will not tell you, but you do need to know what your target is. Otherwise, you're not going to be able to hit it. And you have to be able to think about this. I thought Bushen's paper on security was an excellent example of a whole bunch of non-functional requirements around security that described and specified this is the security level we expect. Much, much easier both for the developers to achieve that quality level and for testers to verify whether it's been achieved. So specifications, and then you go into the design. You'd have design reviews, you'd have testing specifically to catch design problems. And again, this usually wouldn't be testing of a customer workflow. This is testing designed to look at, is this interface talking to this other interface? So you got all these quality gates. And then you have the functional testing, and you have the coding, and you have the unit testing. So lots and lots of gates. And that added up to a quality strategy. The other major part of the quality strategy was a risk analysis. There was a paper earlier in this project about pre-mortems, and a pre-mortem on the product is what we called a failure mode effect analysis or a risk analysis. How could this product fail? And if it did fail, what would probably be causing that? So what do we want to build in to make sure it doesn't fail? I did one product that was a treadmill. It was controlling a treadmill that was being used for a stress exercise test. And we're looking at, well, one of the ways this could hurt a patient is if the treadmill stopped suddenly, or it didn't stop when we told it to stop, and the poor person is, having an event, and they're going to fall over, and we can't, and this treadmill doesn't stop. So we designed in three completely independent ways to stop that treadmill. And we were very glad 6 months later when it turned out one of them wasn't technically feasible that we had two. So, and the customer had only asked for one. But that's the kind of thing you do, is when you've got something that's life critical, is you're looking to design in ways that you can be sure that it's going to work. So the quality gate, this is a typical set of exit criteria for a quality gate in medical products during the 1990s. So we're compiling, we're looking at the complexity, we're running all the unit tests. You notice we're saying we're passing all the unit tests. You can't go forward until you pass them. And 100% path coverage. I'm still surprised by seeing so many people writing, you go on the internet and they talk about unit testing. Oh wow, would 75% line coverage be good enough? Well, if you want to be sure that it's going to work, no, it's not. And it's frankly a lot less trouble if you do 100% path coverage, and you should know the difference between path and line coverage. If you do 100% path coverage or near that, then anything that happens later on during testing is not a stupid coding error. It's something else. So this makes it easier. Doing unit testing, you're looking at one little piece of code. Anything that's going wrong in there, you're going to be able to find it quickly and just rule those out. So And we did this with hardly any tools. So that's still being done today. This is a definition of done from a medical products, not Hewlett-Packard, a different company. It's in my paper, the citation for it, from 2016. Very nice paper written by a man named Herman. And their definition of done has the quality gate. And as is typical in Agile, they kind of mush the quality gates together. So they have the specifications for getting through design, coding, acceptance testing, and a quality gate for defect fixing. That our defects will have enough information in them to do a root cause analysis later on. It will say how the defect was fixed. So, so this is still, this kind of gate approach is still used. It's just handled a little differently in Agile. And they also had the extensive unit testing going on. So what this adds up to, so I've talked about testing, and a lot of the reviews in the testing isn't building quality in as much as it is testing quality in. So you can think of the whole thing like you've got activities that you're doing, and you've got the requirements, the specifications, design, coding, and they're all creating defects. And these defects are pouring into your product. The longer they sit in your product, the harder they are going to be to fix, and they have an alarming tendency to meet each other and have babies while they are in your product. And one bad assumption leads to another bad assumption. So the initial response to this was do a lot of system testing, get to the end, and then just do everything the product can do. And back in the day, 30 years ago, when you had little simple products, this probably worked some of the time. But you still ended up with the user finding some of the defects. So the whole test strategy thing I just showed you basically is adding a lot more drains to this bathtub, earlier drains. This is what I think of as shift left, is you're going to do different kinds of testing and reviews earlier that are aimed at finding the particular types of defects that are caused in that stage. So the types of tests you do for requirements defects are not the same as the types of tests you do for unit test for code defects. If you rely solely on unit testing, you'll miss all the requirements problems. If you rely solely on system testing, you will test and test, you can test in years and still not find everything. It's you do the math, you see it's not feasible. So you can reduce the number of defects going out to the user by doing all these earlier testing and different types of testing, but you're still going to have a bunch of defects, you're still going to have a bunch of testing. So the next strategy you use in a high reliability field is turn off the water. Stop making so many defects. And that's what I'd like to talk about the next 10 minutes or so, is what are some ways to not make defects? And this is, I think, one of the least documented subjects in software development, is how do you stop making mistakes? And it's odd because it's so important to all of us. And what I did was gather together some of the strategies that I've seen used over and over. I'm not going to pretend that these are the 5 best strategies or the 5 top strategies, or that you'll find this list anyplace else. There's a couple of references in the paper to books that do talk about this topic, but they're pretty few and far between. And some of the better materials actually buried in books about project management. And particularly some of the Agile project management books will have whole sections on really good defect prevention practices kind of stuck inside. Which, how many of you are in here are doing Agile? Not some. And how many are doing waterfall? A couple. And how many are doing something kind of in between? Yeah. And so it can be kind of depressing when you're reading an Agile project management book and it starts out like, you absolutely must have sprints that absolutely end in 2 weeks and ship stuff. And you get depressed enough at the beginning, you may never get to the chapter that talks about how to prevent defects, which is going to work no matter whether you're doing Agile or waterfall or something in between. So here's 5 good strategies. Making the structure visible, mistake proofing, maintaining intellectual control, education about your domain, and designing away the chance to make mistakes. I'm going to talk about each of these. So first, making the logic visible. This is how I started out programming in the 70s in college with the cards. Some people are laughing. Okay, who's ever actually used punch cards? Yeah, just a few. The rest of you lucky. Okay. So even this little fragment of code is hard to follow on punch cards in Fortran 4. It's and if you drop the cards, it's even worse. So somebody very brilliantly figured out how to built a machine you could feed the punch cards in and it would print the listing. And the listing was a big improvement in visibility. I can sit down and look at my code all in one piece. And I can take my extremely high-tech tool, the highlighter pen, and mark it up. I'm going to go to line 106. And here I'm going to go to line 105. And here I'm going to go to 106 again. So what do you not see in this fragment of code?
Comments.
Well, it's got comments. They're right here.
Yeah, there you go.
That's a Fortran comment syntax. What else do you not see?
No hierarchy or like formatting of the...
There's no indentation. What else are we missing?
Something that functions.
There's no functions.
No else. Logic is coming.
Yeah, there's no if then else. What's with all these go-tos? I mean, I can go to anywhere from anywhere. That is actually a good way to make a tremendous number of mistakes. So the if then else was one of the early additions to programming language to prevent errors. You can't go anywhere from anywhere. You have to follow this logical structure. So the visibility and this mistake proofing with the tool, the compiler, helps you not make mistakes. And then the indentation, when I started in quantum chemistry doing a lot of Fortran programming, and my professor there felt that real men did not use indentation. And so we had to turn in everything just lined up against the edge. And then when I switched to computer science, I was disabused of this notion very quickly. And you can see how much better the visibility is, and how now with my high-tech marker pen, I can see what's going on. So we stop creating so many defects. And today, you have some very nice tools for visibility. Most of the development environments now do all this color coding, and it's just awesome. And that will help prevent problems. The mistake proofing usually takes you to think about it, you to think about what tool you're going to use. One of the ones I've seen in my career that I liked the best was, writing printer drivers. You've got to install them onto the PC, and you install 3 or 4 printers on the same PC. You've got all these configuration files that are having to coexist. It is possible to have a configuration file that installs one printer fine, and you install a second printer, it fights with the first one, and now they both don't work. And that is hard to debug. And sitting around installing printers on top of other printers manually is extremely slow. So one of the developers involved with this wrote a nifty test tool that would run through all the configuration files and check for configuration file errors. That's what you're getting, was a bunch of the lines were blank or things were missing. And so ran through these, and he's just generating defect reports like crazy. And after several weeks after writing this, the same developer came back with a mistake proofing tool. It was a wizard that would write the configuration files for him. So one of the people who had just got really tired of fixing his problems, and this is something over my career, I've found that if I have something to do that's tedious and repetitive, and I'm going to have to do it 5 or 6 times, I think about, would it take, could I write a tool for this? And if I could write a tool, would it take me longer than doing it 5 or 6 times? And eventually I figured if I could break even, I would write the tool, because I would almost always learn something interesting writing the tool, and it would be more fun. And sometimes I would get a tool that would actually prevent future errors. Once they had this wizard, the error rate went way, way down as you type in the basic information about the printer, and it would spit out a perfectly formatted Microsoft compatible, up to all the specs. And it took some testing to get it to the wizard to work, but once it was in place. So that's the kind of thing that really helps maintain quality, is to be thinking about, could we prevent our most common errors by automating some part of our process and mistake proofing. Then maintaining intellectual control. I think of this as, don't try to eat things bigger than your head. Your brain can handle the relationships between approximately 7 things at a time. There's some variation in that, but psychology studies have shown this over and over. You get much over 7, you start losing track of how things connect to each other. So what is something you would do if you had a piece of code that had gotten beyond that limit? What would you do?
Break it up.
Pre-edits.
You'd break it up, you'd refactor it. Yep. So very common technique. Some other things that help when it's too complicated is using abstractions that will simplify what you're looking at, so you don't have to look at all the stuff going on at once. When object-oriented programming first came out, that was the huge advantage of using objects, is the classes and objects hid a whole bunch of what was going on, so you didn't have to look at it. You just looked at the high-level behavior, and then you could talk about the high-level behavior connecting to each other. So a way to make things simpler to maintain intellectual control. Design notation does about the same thing if it's used well. Data flow diagrams, high-level picture, and then take each piece and look at it, and that is because you're making a high-level picture, you can only have so many arrows on that sheet of paper, so you're limiting the number of connections you can have simply by using that notation and that design method. And it's forcing you not to have a whole spaghetti thing going on because you've got to draw a picture. I've also seen that work in process development, is you get people to draw a picture of what they've got, a flow map of their process, and they've got these arrows going everywhere, and they go, oh boy, no wonder we're having trouble. Maybe we should simplify this. Yeah, so start grouping things together. Design patterns. This is a really good, also an abstraction method that helps you think about what you're doing in a way that's high level enough that you're not getting confused, and has a nice, clear, uncoupled way with boundaries around it to go and look at what's going on inside without having to worry about the outside world. So this maintaining intellectual control is really key. This was one of the key things in the clean room methods of attaining software quality. And test-driven development, I've thought about this some. It's a really powerful method for doing high quality start to finish. I wish I had known about this 20 years ago. It does work outside of Agile development. It works just fine in waterfall development. I really encourage any person who's starting out development today to learn test-driven development and look at whether you can do it, whether or not you have X unit, whatever unit tool. I've done one successfully where I was writing in Perl and all I had was Perl. So I was writing little unit test scripts in Perl and then running my scripts. I was writing a metrics management system. So test-driven development, you write the test and then you run the test. So you're finding problems soon after you create them. You're fixing the problems immediately. The test-driven development method requires you to do that. I actually don't know whether this prevents creation of problems. And how many people have used test-driven development yourself? Quite a few. So do you feel that it helps you prevent problems?
A lot of them.
And how does it help you prevent problems?
Well, I just over and over again, I'm writing a unit test. Like, well, why is that failing? Look at my code. Oop, typo.
Mm-hmm.
It takes care of it right away.
Yeah,
There's
so
a whole class of problems.
So you're finding the problems right away, and you may end up discovering that you either learn not to make those particular mistakes, or you come up with a way to prevent yourself from making them. So the fast feedback is really helpful. Fourth method I want to talk about was know your domain. And this, again, seems like a no-brainer. Why would you start using a new technology or a new language without knowing anything about it and just plunge right in? Well, I've seen managers tell people to do that. I've seen them say things like, well, SQL is just another programming language. You know C, you'll be fine. Not the case. So there's lots and lots and lots of ways to get education on a technology. People who are trying to build quality in pay attention to this. And in my older paper from 2007, I have several examples of how to use a project risk analysis to drive justification for somebody to spend money on you to get you the training that you need. So you can read the older paper. Those examples still work. And then one of the most powerful things is designing so that the opportunity for error is just not there. I've got two examples here. This first one is from James Shore's The Art of Agile Development, which is a very good book. And he's giving an example. If you have a user interface and it's going to be pulling, say, names from a database, and the database fields have a certain length, so pretty obviously your user interface needs to have at least that amount of length also. So, one of the obvious things you could do there is the beginning coder. You go look at the database specification and copy, see, wow, the maximum length is 128 characters. I'm going to go type that into my program. And, gee, I think I'll also write an acceptance test that will allow me to check whether that actually is working. So what do you think is going to happen?
256 characters.
But how can you put 256 characters into a database that's defined at 128?
Oh, well, the database changes.
The database changes, yeah. So second thing you could do is, as James Shore says, write a tool that will go through your code and go through the database and check that they're still in sync. This is not bad. That this would be a good preventative method or a good testing method. But the preventative method is the user interface goes and looks at the database and says, yay, verily, it's now 256. Great. I'm going to draw a field in here that's 256, and maybe I'm going to have to wrap it around to make it fit on the screen. But by George, I'm going to have that length. And that is, that's designing away the opportunity for that error to happen. A second example of the same thing at a higher level is printers used to come with these install sheets and install posters, and they'd have pictures, little screenshots, and then you have a screenshot on the screen. Yeah, I see some people laughing like you remember what would happen when you opened up and you used this, figuring you didn't actually throw the poster away, which about half the people do. But if you actually read the poster, you tended to find that they didn't actually match what was on the screen because
Watch, plop, plop.
No,
because
yeah, I still see that today. I go to a web page and it says, you'll see this and this and this, and it's nothing like what's on the screen.
Yep. Yeah, the poster went to print before before the screen was designed, but it wasn't actually finished. They had 3 more weeks. The poster was in print, and they changed some more stuff, probably for good reasons. Well, the human factors people came and looked at this and said, we could design away this opportunity for errors. Why do we have these screenshots on this poster in the first place? Number one, half the people never read the poster. And number two, is it really doing anybody any good? So they run some tests with users to see what users think. And in fact, the users were pretty happy with a poster that just said, make sure your PC is on. Connect this cable to this cable. They really like the pictures of the cables. An awful lot of people do not know what the names of cables are, and they want those pictures. But beyond that, it's like, get it hooked up, and then I'm happy to go look at my laptop. This is designing away an opportunity for error, designing away a problem for users. So that was all stuff that we did in Waterfall. And we had all the quality gates, and we were using these preventative methods. And then comes along Agile, and basically that big huge V goes away, and we get this little teeny, a whole set of little teeny V's. So we're still doing the same activities and a lot of the same testing, but we're doing it in very short increments. And this has some huge advantages. The biggest advantage is that this process of writing these huge requirements and specification documents turns into simpler user stories because you're going to code them right away. You don't need as much documentation. You're not going to have 3 different organizations you pass them through before they get to a coder. The same people are going to be writing the user story and doing the coding. And then you're going to go within 2 or 3 weeks to a user demo. So that's replaced a lot of the acceptance testing. Show it to users, see what they think. If you're wrong, then you're going to find out about it right away, fix it right away, and you've prevented this bug breeding thing in that you made a lot of assumptions and built this whole huge user interface based on these assumptions. You find out quickly. So that's a big improvement in quality control from Agile, is the user demos. And the continuous integration is actually mainly because the tools are better, that you have the hardware to run a build in less than 8 hours. This was a huge luxury in 1998, and you keep doing the compile over and over and some automated tests over and over. You're getting all the compile errors reported immediately, and again, a really short feedback loop. So most people doing Agile lump they still have many of the same quality gates. They lump them together in the definition of done. The first few years of Scrum, this wasn't happening. There wasn't any definition of done. And we saw people just throwing out quality gates and then being sorry. So having a good definition of done and a good team operating agreement so that you've got those gates. And that I often check them against the old definitions of gates to see if they've covered all of the types of defects you can get out of all the activities. Because your definition of done shouldn't be saying simply, oh, we did system testing. That's not going to get you high quality. So how many of you, a number of you said you weren't actually releasing at the end of every sprint. How many are not releasing at the end of every sprint? Yeah, we got some. So if that's your situation, I'm not going to tell you you should be a pure Agilist or whatever. If that's your reality, then you're doing something else between the end of the sprint and the actual release, doing some type of activity. Maybe it's deployment, maybe it's translations, whatever, internationalization. That implies that you have another quality gate, that you did something, so there should be another gate. If you call them both definition of done, you're just going to be confused. And I don't like done for the same reason. Language should help you talk to each other, not confuse you. One of the better solutions I've seen is from eBay. There is a good paper on this in 2015. So again, a reference. And they did 3 definitions of done where they specified the level. So for Agile, how it affects software quality, the fast feedback and the focus on the user and customer has, I think, really improved quality.
I'm sorry. Are there any drawbacks to actually using the Agile method that you were describing? Like if you have so many more gates and more methods for checking it, is it more cost effective, more process effective just to use that method, or is there actually something that you find negative? I'm sorry.
So if you're trying to get high quality and building quality from the beginning, you do want to focus on prevention because lots and lots of testing is expensive. But that means you're focusing on prevention and finding things rapidly means you have some kind of check going on at each step after the user story, after the design, after the coding. They don't necessarily need to be very long. When you're working on a single user story, those can be really fast. That can be a half-hour activity. But you have the gates there. If you take out too many quality gates, then you end up missing a bunch of defects because you don't have anything that's specifically looking for design problems because you got rid of your integration testing and figured you didn't need it. So you're, does that answer the question?
Not really.
Okay.
Sorry. It just seems like you were basically saying the Agile method was just a strictly superior system. Is that?
Depends on what you mean by Agile. Depends on what it mean. I'm not convinced that Scrum by itself will solve all the world's problems. I am convinced that doing things in increments of much less than 18 months is better overall. So you can do stage delivery, for instance, which has much less of an iterative approach than Scrum does, and you might have longer, you might have 4-week or 6-week stages or increments, but the cadence and the small batch size really, really helps. And whether or not you can get them to releasable. Anytime you're not getting it to releasable, Agile is forcing you to think about why isn't it releasable, what have I not done, and how am I going to account for that in the work planning. Am I letting my whole group go ahead and start new features when these features are clearly not done because they're not at releasable quality? If you're simply putting things on the shelf, they are releasable quality, but you're just not going to release them yet, that's a different story because they are done. So understanding what done means. Another thing that's been problematic about Agile is that the non-functional requirements in a lot of groups got lost. And if you go out and look at Agile literature today, you see at least 3 different ways to account for non-functional requirements. And that is not entirely useful because it means there's no consistent agreement, and that means some groups aren't doing it at all. And then they are surprised when they have mysterious problems that trace back to design errors. Well, that's partly because they didn't have non-functional requirements stated well in the first place. And I talk about that more in the paper. And the same thing about user demos are not going to go in and find design problems for you. They'll tell you if the user doesn't like your general idea or the features, but they're not going to tell you you've got security problems. So those are some problematic things. A lot of these practices that came in with Agile actually can be used in waterfall or semi-waterfall projects. And the place you'll read about them is in Agile, like pair programming, but they do work in other projects as well. So that's my paper. Is I believe that to get really good quality, you build it in, and that is actually faster and less expensive than trying to test it in. And you're taking a couple major strategies. You find your problems early, fix them right away, and focus on prevention. So you're very thoughtful and disciplined about thinking about where are my defects coming from and how could I not have these. And we've talked about 5 different prevention strategies that you could use, and there's a couple more in the paper. Also talking about quality factoring and how you get non-functional requirements implemented throughout your design, which was something that simply wouldn't fit into this talk. So that's my talk. And do we have any time left for questions?
Any questions?
Yeah.
What would you say if you're trying to find a world where sometimes it's okay to not have, you're not building for NASA, it has to work right the first time.
Mm-hmm.
When do you find that? Is there a simple way to think of that in terms of how far do I have to take building in quality before the customer sees something that's pretty inexpensive testing at that point, if that's a non-lethal to your customer base?
Mm-hmm. And the question is, how do you find the balance? So I have 2 tools that I think are really useful in finding a balance when you don't need 100% totally awesome quality, is the non-functional requirements, defining what your quality targets are, how much reliability is acceptable. The statistical approach we were seeing in one of the papers yesterday was really talking about it's okay not to have 100% reliability, so how do we define reliability? And he was using statistics to help specify. And another good way to talk about that and think about that is a defect severity rubric. So this is like a chart that says, for this type of problem, here's an example of a low severity, here's an example of a medium severity, here's an example of a high severity. This sounds really easy until you sit down and do one. And I found with groups that when we insisted that they sit down and do one with their marketing, their product owner, marketing folks, it ended up having some very helpful conversations about what would be truly severe and what would be, yeah, not so bad. And that would then drive some of the both design and testing strategy. For instance, you've got user interface and you've got a phone number on there to call. You put the wrong phone number on, that's actually a critical defect in a product that's sold at high volume. Whereas if things run off the screen a little bit on the edge in 2 languages, yeah, as long as you can still read the instructions, it's not as critical. So you sometimes found stuff that as developers we're going, whoa, really? That was, you think that's critical? Uh-oh. I better go take another look at that one. Other questions? Okay, you're all...
Please do the evaluation. Come on your mobile app, do the evaluation. Thank you very much.